Now we will discuss about the uh, ba- basis uh, basis of a topology or uh, base base for the topology tau over a set X, non-empty set. We first define the definition of the basis, simply basis or open basis, because the basis on closed set also can be defined in some conditions provided. But we mainly discuss the basis on open set. Actually, the basis is a collections of a family of open sets. Uh, definitions. Definitions are collections beta. Beta is the collections are noted as beta basis notations of subsets of a set X is called an open basis base or basis for some topology defined on the set X. When the collections beta of subset of a set X will be a basis if it satisfies some conditions. If the following conditions are satisfied. Which are the conditions? Number 1, phi a null set belongs to the collections beta. Number 2, for each element X belongs to the set X, there exists uh, open set B belongs to the collection beta such that X belongs to the open set B, that is, the set X can be written with the collections beta. This is open set. This is point of a set. This is base, but now it is a collections. Of subset. set. If this condition is satisfied and the last conditions, if B1 is open set, B2 is open set, both are belongs to the base or collections family beta, and X belongs to B1 intersection B2, there exists B3 another open set in the collections family beta such that X belongs to B3 is a subset of B1 intersections of B2. If three conditions are satisfied, then we will say that these collections, these collections will be called base. This is the definitions of basis or base. The next question is how can it is related in the topology. The base for the topology defined on set topology tau on X. The topology, some topology where tau on X, defined on X. The topology how related? It is a question. X tau is a topological base. Okay. Actually, the relations with the base is a family of open subsets of the set X, and that every open set of the topology wait a minute. Is equal to the union of subfamily of it. This is the relations. It is just if you say in a one line, it will be that relations between basis and topology. The relations a basis is the collections of all finite intersections of subbasis elements. We naturally define basis over an open set. So the open sets in a topology are all possible union of basis elements. That's all. So open set in a topology are all possible union of finite intersection and subbasis element. The next questions may arise basis in topology is unique. The topology defined by base, a topology uh, defined by a base beta collections or family is uniquely determined by that base. But I want to ensure you that this is a topology. It may have basis 1, it may have basis 2, it may have basis 3. It can be defined by uh, many bases. The next question is T is a topology. Always it is defined on over set X, non-empty set X. Topology on a set X is itself a basis on X. Yes, but it is the definition is trivially satisfied. The definitions is trivially satisfied. Okay, the next questions, easy questions, basis of a discrete topology. The collections beta is equal to the element X belongs to X, is the basis of a discrete topology. We come into the point that these elements are singleton elements. So we can come into the point. These singleton elements, this is covering the whole set X. Take the union of its. So in discrete topology, we conclude that the every singleton elements of the topology is the basis of the topology. In a roughly speaking, you can think about that basis is such a pattern or such a method that you can make it or define the whole topology with a few collections. That's all. And in such cases, the things uh, that the topology tau has many bases. It may happen, but you can mind it. But a collections beta basis generates a unique topology. Unique topology. Sometimes some trivial questions may occur that is the collections beta basis can be a subset of the topology. Yes, it can be a subset of the topology. So uh, next we want to check about more on this place, but before come to this discussions, we can say that in discussions of real number sets, real numbers, here the every open intervals are the basis of it. uh, uh, Actually the base for the topology which are easier to describe than an arbitrary open sets, but the most important topological definitions such as continuity and convergence can be checking using only basis open sets instead of arbitrary open set. In such cases it is the application, but some topology have a base of open set with specific useful properties, and we will learn it after few discussions. But the things I want to say, is it possible to define and close sets or not? These are very important questions. But I don't feel more interest on define and close set. But I write down closed sets are equally adept at des describing the topology of a space. X is a set, tau is a topology, forms a base for closed sets. Forms a base for closed sets. If and only if each closed set A and each points X and not in A, not in A, not in A. So there exists an element call it C containing containing A but not containing X. A family C is the base for the closed set. Now, C, B, base for the closed sets of X, then it satisfied two conditions. Two conditions. One, intersection of C is equal to phi. Number two, for each C1, C2 belongs to the collection C and the union C1 union C2 is the intersections of some subfamily of C. So what is the fact? That is for any X belongs to X. If you will think that not in C1 or C2, so there is some C3 containing C1 union C2 not containing X. That's all. So any collection of subset of X satisfying this property forms a base for the closed set of the topology on X. So the closed set of topology are presently the intersection of the members of C. In some cases, it is more convenient to use the base of closed set rather than the open ones. A base is completely regular if and only if the zero sets forms a base for the closed set. That's all. Now, we will go to the points of the theorems. Let me one moment. Yes. Theorem. Let beta be a base for a topology on a set X. Suppose topology tau on beta basis consists of those subset G of X for which corresponding to each X belongs to Z, there exists uh, bx belongs to beta, such that x belongs to uh, x belongs to b of x subset of z. Then tau beta is a topology on X. Proof: it is a topology, so phi belongs to uh, tau of beta. It is obvious. The conditions is by default it have already been there. Again, x belongs to x. There exists a b belongs to beta, such that x belongs to b, x belongs to b subset of x. Actually, as beta is a cover of x, implies x belongs to tau of beta. Now g of alpha is indexed set subset of tau beta. Uh, then uh, then x belongs to union of alpha index set g of alpha implies ax belongs to g alpha for some alpha belongs to index set. It implies there exists a b belongs to beta such that x belongs to b subset of g alpha 1. Why g alpha 1? Because since g alpha 1 belongs to tau of beta, subset of alpha belongs to the index set is equal to g, implies these collections will be tau beta, implies union g alpha belongs to index set it belongs to tau of beta, hence the result. Again, we have to prove that this is a conditions are satisfied by the topology. Then this will be the base of the topology. Now G1 and G2 belongs to two elements tau beta, because this is we can guess it, and X belongs to G1 intersection G2. It implies there exists a B1 element B1 B2 belongs to the collections family beta, such that we can even like this B1 subset of G1 and X belongs to B2 subset of G2. What the fact? X belongs to B1 intersection B2. Yes, implies G1 intersection G2. It implies there exists a B3 belongs to beta, such that X belongs to B3 subset of B1 intersection B2 subset of G1 intersections G2. That's all. We come to these points. We are just checking that these are the base. We confirm it. So what happened? The things is that is X belongs to B3 subset of G1 intersection G2, where B3 is also a collection belongs to the beta. B3 also a collection on the B3 beta. G1 intersection G2 belongs to tau beta. Hence tau beta is a topology on X. So what do we get this information? That the base forms a topology, or a unique topology can be distinguished by its base. But a topology has not only one base, it may have many bases. If beta is a base for the topology on a set X, then the topology tau beta describe that the topology is called an open basis for simply a members of tau beta well. Then these basis open sets as a relations on the topology, and so we think that the base and topology has a relations, and this is established by these theorems. Again, the most popular theorem, another theorem. This is the theorem let the topology tau on a set X be generated by an open basis beta, then the member of tau are precisely the unions of members of beta, that is sorry, that is let G belongs to tau. It's both imply G is equal to union of B collections of alpha belongs to the index set. Okay, yes, where this B alpha belongs to beta, the collections for each alpha belongs to the index set. That's all, and this is a index set. That's all. The things we will prove that members of tau, the members of tau are precisely the union of the members of beta, and the collections are precisely possible to express. Similar, we will take it the obvious positions for the topology, that phi is always in the topology. So since phi belongs to the topology, And the topology tau on a set defined on a set X, actually any union of members of beta is a members of tau. Yes. On a set X, any union of members beta is a member of tau. Conversely, let Z belongs to tau where G not is equal to non-empty set. For any X belongs to Z, there exists Bx belongs to beta such that X belongs to Bx subset of Z as X runs over G. We have G union of X belongs to G B of X subset of Z, then Z is equal to union X belongs to Z. This is the Bx. Okay, yes, that is G is the expressible as the union of those members of beta. The case Z is equal to phi is obvious if you will think, but we will prove the second part is not equal to phi. And in this positions, when we will discuss, then phi is equal to the collections beta. That's all. So the theorem is proved that members of tau are precisely the union of the base. If you will, it is not a. If you will draw this picture, it is not the proper, but I will try to understand it. If this is topology, if you just imagine it, it is not a true picture because it is truly complicated. Uh, these are the base. These are the base. These are the base. This is a B1. This is a B2. This is a B3. This is a B4. B5. B6 and B7. You can write down sometimes it's a BA beta because it's sometimes you may think that it will even collections of it, so it may sometimes be true or sometimes false, but here we will think that all are B, so tau is equal to the union of the collections of B1 union B2 or union B3 union union B7. This is the union of it. This is the topology tau defined. Why it is complicated? Because we don't know the locations of the points and location of the phi, and in some cases they are overlapped because any two elements of this will again and other collections. In such conditions, we cannot express by graphical representations in plane. So I think this is imagined to realize or understand it, nothing else. It is not exact picture and not possible to draw because some issue are arised. Again, nice questions will arise. If a topology, tau is uh, uh, defined by the collections, unions of beta collection base. Now the questions may arise that this picture have 7 base. Okay, 7 base. It will be expressed the 7 base forms this topology. It may be happen that it is only 3. Tau is union of tau I is equal to 1 to 3. It may happen. It is a great question. Yes. What is the questions? The questions it tells us this is a very nuisance question. The questions tells us that a topology can be defined by many bases, uh, but the base is the union of the collections of the base is the smallest topology. Yes, it's ensure that these collections of base, only the collections of bases gives the smallest topology. If you will add it, no issue. But this is the enough. This is a sophisticated, and this is enough to describe this topology. And this is the smallest topology. Unless you will add, suppose you will add beta 5. It also express this topology. No issue. But if you will take the bases, these bases will be the smallest basis to describe a topology. That's all. No problems. And now, again we will describe a theorem. X tau topological path. Yes. And beta be a subcollections of tau such that every members tau is the union of some members of beta. What about on beta? What we can say that beta? We talk about that open basis, closed basis, but these things ensure that then beta is open basis. If this is satisfied, then ensure us that beta is a open basis. To show this, we first show that beta is a base for the topology, and x X is a element X is a element in the topology, and X is equal to union of this is index set and B of alpha. For A sub collections, B of alpha belongs to index set of beta. Thus, union of beta is equal to X. Let a moment. Oh, B1 and B2 belongs to beta. B1 intersection B2 belongs to beta. Now B1 V2 belongs to tau, since beta belongs to tau, and hence B1 intersection B2 belongs to tau. Thus, we will give another subfamily. We will just write down B of alpha is equal to union of B of alpha. No, not this is true. Collections of B of alpha belongs to index set, is for the collections of B alpha belongs to the index set. If you consider another index set, this is Bi, subset of B1 intersection B2 for some I, and such Bi belongs to beta. Guess it. Consequently, this beta is a base for some topology tau. So we will think that this is a topology tau. We need to prove that tau1 is equal to tau. In fact, U belongs to tau1 implies U is the union of some members of beta. Yes, so U belongs to tau. Why? Yes, because since beta belongs to tau, again V belongs to tau element. Imply V is equal to union of B alpha in some collections alpha. Some collections of alpha, it's a defined V. collections of alpha v uh, where each I belongs to no alpha belongs to index set, some index set, uh, can show that v belongs to tau 1. Yes, this is also belongs to tau 1. Uh, so uh, that a topology can be described by basis, and the basis is the smallest collections of the topology. So it is obliged to tau is equal to tau plus, because two conditions are inside it. One is basis uh, represents a topology. Number two conditions, um, basis is the smallest collections. That's all. Combined to this, t is equal to 2 plus. Now, uh, in a similar manner, we'll think about that this is the basis collections of a uh, uh, open set, but it may have any sub collection. Yes, there may have sub collections. We now define of some sub collections, properties of sub collections, and later on we'll get the discussions. Talking about sub collections for any topology, tau on a set X, any sub collections of tau is an open base for tau. If and only if every member of tau can be expressed as the union of the members of the collections of family beta. Equivalently, we can write this is if and only if conditions z belongs to tau and x belongs to z, there exists b belongs to beta such that x belongs to b subset of z. Actually, we get a criteria. The criteria is that for the comparison of two topology, given set in terms of their basis. Another theorems, but our discussions have some changing. In the previous discussions, only one collections define one topology. Now we'll discuss there are two collections. They define two topologies, and what is their relations? So collections B define topology tau. B1 define topology tau1. The great questions is that the relations of comparable. Relations of comparable. Yes, we already know about it in the last lecture. Tau is a finer than tau. Tau1 or tau dash, whatever may be, it's no issue. This tau1 is finer, not that, finer than tau. What is the meanings? We have already discussed. Tau1 is stronger than tau. These two are topologies. What will the effect on base? What will affect? If and only if the effect is x belongs to, for each x and each b belongs to the collections beta containing x, there exists a b dash belongs to beta dash such that x belongs to b dash subset of B. These relations will arise. If these conditions is arise for the base, we can define about the relations of finer or coarser between two topology. We consider an examples. Consider the collections beta of all circular region on some topology tau. Again, the beta dash is the collections upon rectangular region inside a rectangular region inside a circle or a sphere. Okay, and this circle region inside a plane. Topology tau. Topology tau dash. From the two figures, conclude that this topology of two are the same. For true topology, culpates are the have differently the pictures. Now, we'll discuss more about it on continuous derivative functions. It is to be too much difficult, but I will discuss it now. Okay, let me left it for exercise. Epsilon equal to z 0 to 1 mod f minus c mod less than epsilon.